Welcome to the deep dive. Today, we're taking on a mission really to understand how large language agents might become truly autonomous. Learning from the world without always needing that explicit thumbs up or thumbs down.
Hmm.
We're diving into sources presenting this novel concept called early experience. It's pitched as a way for agents to train efficiently, scalably, and importantly, without traditional reward signals.
And that lack of reward, or rather the difficulty in getting useful reward, that's the central challenge, isn't it? We want agents navigating complex places, websites, multi-step tool use.
Right?
But those environments, they rarely give you a clear score right away.
Uh-huh.
Or the task is so long, like booking a complex trip, that getting a successful example for reinforcement learning is just, well, computationally huge.
Yeah.
Very expensive.
That really throws the spotlight on where we've been stuck. For a long time, it's been the era of human data, mostly supervised fine-tuning, SLT imitation learning.
Showing the agent what the expert did.
Yeah, in state A, do B. But the sources point out a big problem. The agent only sees the perfect path. It never learns from, say, its own potential mistakes. So, generalization, trying something new, it struggles.
That failure to generalize is the killer. The moment the agent steps off that narrow expert path, it encounters states it hasn't seen, and performance often just collapses.
So this is where early experience comes in.
Right? The research presents it as this potential solution, a scalable, reward-free middle ground, sort of a bridge between just copying experts and the full, often difficult, reinforcement learning approach.
Okay, before we get into the two specific strategies they explored, I'm still thinking about the mechanics of reward-free. If there's no external good job, how does the agent actually generate a learning signal? And, are we just creating tons more data to process by letting it explore like this?
That's a fair question about the data load. The core idea is pretty elegant, actually. The future states that result from the agent's actions. Those become the supervision signal. So, early experience is interaction data from the agent's own actions. But the learning comes from observing the environment's dynamics, what happens next, not from an external score.
So it's about learning the physics of the environment it's in. How does that interaction data get structured for learning?
It starts from a state in an expert's path, let's call it SZI. Then the agent thinks, okay, what else could I do here? It proposes alternative actions, SZI, Deller.
Right.
Then, and this is key, it actually tries that alternative action in the environment and sees what happens. It observes the next state that results, SZI.
I see.
So the learning material becomes these triplets: the original state, Deller, the agent's alternative action, LZ, and the actual resulting next state, ETRC. This collection teaches the agent cause and effect. If I try this, then this specific thing happens.
Okay, that makes sense. And the sources indicate they tested two main ways to use this self-generated data, right, across different models like Llama and Quinn. Let's unpack strategy one, implicit world modeling, IWM. What's the core goal there?
IWM is all about grounding the agent's policy in how the environment actually behaves, teaching it, if I take action X, what will the world look like next? It's building an internal, predictive sense of the world.
And how is that implicit? How does it work inside the language model?
It's framed as an auxiliary task during training. The agent gets the state action pair it tried, AO2, and its job is to predict the next state it observed.
So like if it typed a wrong date on a website form, it learns to predict the exact error message that would pop up.
That's the idea.
Yeah.
It trains itself to predict the specific consequence of its actions, good or bad.
Which means it's not just memorizing the one right way, it's building a kind of predictive map around the choices it considers.
Yes, that integrates prediction directly into its policy learning. It acts as this valuable warm-up. It makes the agent more robust when it inevitably encounters situations slightly different from the expert data later on.
And practically, how is it implemented?
It's usually a two-stage thing. First, train with this IWM objective, learning the world dynamics. Then you fine-tune on the original expert data.
Okay, that leads us to the second strategy, self-reflection, or SR. This sounds less about raw prediction and more about, well, reasoning, improving decision-making.
That shift from just predicting to actually justifying is the core difference. SR focuses on learning from those suboptimal choices to generate grounded rationales.
How does SR turn just observing a different outcome into a useful learning signal, again, without a reward?
It's comparative. The agent looks at the outcome of the expert's action, SI plus $1, and compares it to the outcome of his own alternative action, TESI 10. Then, using a language model prompt, it generates an explanation, a chain of thought.
An explanation of what?
an explanation justifying why the expert's action led to a better outcome, based only on comparing those two observed results, SI plus 1 and 10.
Let's use that web shop example from the sources. That makes it clearer.
Sure, so say the expert query is for a blue shirt under $20.
Yeah.
The expert clicks the $15 blue shirt. The agent's alternative action might be clicking a $30 red shirt. It tries this, observes the resulting page state.
Right.
The self-reflection process then compares the state after clicking the blue shirt with the state after clicking the red one. The generated rationale might be something like, okay, the red shirt matches the color preference mentioned perhaps, but the state shows it costs $30, which violates the under $20 budget constraint from the query. The blue shirt state shows it meets both.
Ah, so it's not just red shirt bad, it's turning the observation into an explicit principle.
Constraint.
Constraint violation.
Yeah.
Budget exceeded. That seems really powerful.
It provides transferable supervision, yes. It's learning the why. The training for SR then involves jointly predicting both this reflective chain of thought and the expert action. It pushes the model beyond just copying.
So it has to understand the reasoning to predict both correctly.
Correct. It forces the model to internalize those decision criteria.
Okay, so they tested these two approaches, IWM and SR, across, 8 different environments. Pretty diverse set, ALF world, science world, web shop. What were the big takeaways from the results? Did early experience actually work?
Oh, yes. The results were quite strong. Early experience consistently boosted performance over the standard imitation learning baseline. And this wasn't just in one type of task. It held up across the board. Embodied navigation, scientific simulation, multi-turn tool use, web tasks. Pretty consistent uplift.
Did the two strategies show different strengths like you'd expect? IWM for dynamics, SR for reasoning?
They did, and the analysis in the sources really digs into this. IWM focused on predicting transitions, gave the biggest boost in environments that are more structured, more transactional. Like WebShop, they reported gains up to plus 18.4 percentage points there over just SFT.
Wow, an 18-point jump just from that dynamics warm-up. That's significant. Did that hold up as models got bigger?
It did. The benefits were seen even scaling up to the 70B parameter models. It suggests IWM addresses a fundamental gap. And conversely, self-reflection really shone where tasks needed more complex, multi-step reasoning and handling constraints.
Where did SR make the biggest difference then?
Tasks like Travel Planner saw gains up to plus 15 points. And in Science World, which involves complex problem solving, SR pushed performance up by, I think, plus 13.3 points on the 8B model. It clearly helps more with the deeper reasoning parts.
Let's talk generalization. That's the weak spot for imitation learning. Did early experience help agents perform better when faced with situations outside their training data, the ODE scenarios?
That was another key positive finding. Yes, it significantly improved ODE preperfidness. Interestingly, the sources showed that sometimes the improvement out of domain was as large as or even larger than the improvement in domain, like on the Search QA task.
What does that suggest?
It strongly suggests that learning from its own exploration helps the agent grasp the underlying principles of interaction, not just memorize specific sequences, makes the policy less brittle.
And this connects to why maybe other methods haven't worked as well. The sources contrasted EE with things like long chain of thought or star-style data generation. How did E stack up?
The key difference seemed to be grounding. Methods like STAR, which trying to generate rationales without actually running the alternative actions and seeing the results, often produced ungrounded, sometimes hallucinated explanations. They occasionally even hurt performance.
Because the rationale wasn't tied to actual consequences.
Correct. Longitude also had issues, sometimes leading to invalid actions. Early experience, because its supervision comes directly from observed state changes resulting from the agent's own trials, led to robust improvements that were grounded in reality.
Okay, groundedness is key. What about efficiency? Does the agent need to generate a massive amount of this exploration data? Is it data hungry?
Actually, the data efficiency was highlighted as a strength. The web shop results were particularly interesting. They found that using just 1/8 of the expert demonstration data, but combining it with early experience data, already outperformed the baseline trained on the full expert data set.
1/8. So the quality of that self-generated, grounded experience is really potent.
It suggests so, yes. It seems much more valuable than just more passive expert examples.
Did they look at how much exploration helps? Like the number of alternative actions, that K factor?
They did. And it affected the two strategies differently. IWM generally kept improving. As K increased, more alternatives meant learning richer dynamics. But SR seemed to hit a sweet spot with a modest K, maybe 2 to 4 alternatives.
Why would that be?
The thinking is that too many alternatives might dilute the contrast needed for a clear, sharp reflection, comparing the expert path to a specific suboptimal one.
Interesting trade-off. Okay, let's bring it back to the big picture. The era of experience, ultimately meaning reinforcement learning. How does this reward-free early experience set the stage for later RL?
Even though EE itself doesn't use rewards, it creates a much better starting point for RL. The researchers tested this directly. They took the models pre-trained with IWM or SR and then applied a standard RL algorithm GRPO using actual rewards in environments like WebShop and ALF World.
And compared that to starting RL from just a standard SFT model.
Right? And the results were consistent. Starting RL from an early experience checkpoint led to higher final performance ceilings after the RL phase.
So the head start it gives actually translates into better peak performance later.
Yes, the performance gap created by EE was often maintained or sometimes even grew larger after the same amount of RL training was applied.
So early experience isn't just a patch for rewardless scenarios. It seems to build a fundamentally stronger, more general foundation that makes future learning, including reward-based learning, more effective.
That seems to be the core finding. It's a practical, scalable, reward-free way to get agents learning from the immediate results of their own actions. By observing consequences, even failures, they become more robust, more prepared.
It really makes you think. The research suggests that just by structuring how an agent explores and learns from observation without explicit grades, we can significantly boost its capabilities, maybe more effectively than some traditional methods. It prompts the question, how much untapped potential is there in simply learning the cause and effect of the world directly?